morning. Here we are going to prove the Cauchy's theorem that states, let D be a simply connected region. Simply connected region means a region which can be shrunk to a point. Then the region is a simply connected region. And let fz be a single valued continuously differentiable function on D. This fz is continuously differentiable. Differentiable means f dash z exists at each point in D, and also it is continuous. Then the integral of fz over the closed contour C is equal to 0. So for the closed contour which is contained in D, the integral of fz over this closed contour C is 0. Right? This we need to show. So for the proof of this theorem, we are going to make use of the Green's theorem that states, if pxy, p is a function that depends upon both these variables, then qxy, then partial derivative of p with respect to y and partial derivative of q with respect to x. If these are all continuous functions within the domain D, and if C is a closed contour in D, then the line integral of p dx plus q dy is equal to, over the contour C, is equal to the double integration of partial derivative of q with respect to x minus partial derivative of p with respect to y. Dx dy over the domain D. This is what the Green's theorem states. We are going to make use of this theorem. So for this Green's theorem, what are the conditions? That all these are continuous functions within the domain D. So for the use of Green's theorem, we need the continuous functions. Right? Okay. Now the integral, we need to show that integral of fz dz over C is equal to 0. This we need to show, right? The integral of fz dz, how can we write this? This to be equal to the integral of, what is fz? It is u plus iota v. If z is equal to x plus iota y, then f of z is u plus iota v. U is a function that depends upon x and y both. V is a function that depends upon x and y both, right? So we write fz to be u plus iota v. What is dz? From here we write it is dx plus iota dy. Very fine. Alright. So further, just open this bracket. We get u dx plus iota u dy plus iota v dx minus v dy. Collecting the real parts, we get u dx minus v dy plus, now the imaginary parts, u dy plus v dx. Or okay, let me write v dx first. It is v dx plus u dy. So this line integral fz dz over the contour C is this. Let me mark this as 1. Now we have, what is the derivative for fz? Because fz is what? It is u plus iota v. So its derivative will be, it is partial derivative of u with respect to x plus iota partial derivative of v with respect to x. You can also write this as ux and this to be as vx. Ux means partial derivative of u with respect to x, right? So I'm writing f dash z to be this, and this can also be further written as, if I use the Cauchy's Riemann equations. What are the Cauchy's Riemann equations? It is partial derivative of u with respect to x is equal to the partial derivative of v with respect to y. and partial derivative of u with respect to y is equal to negative of partial derivative of v with respect to x. These are the Cauchy-Riemann equations. So I can also write this f dash z to be equal to, replacing this with partial derivative of v with respect to y, and replacing this with negative of iota partial derivative of u with respect to y. So these are by the use of the Cauchy-Riemann equations. Please take this as your remark, learn this. Now since it is given that fz is continuously differentiable function, that means its derivative exists at all the points of D, right? And it is continuously differentiable. So f dash z is continuously differentiable. If f dash z is continuously differentiable, then all these exist and are continuous in D. Yes, all these exist and are continuous in D because f dash z is itself continuous in D, right? And it is continuously differentiable. So let's write this further. Because f dash z is continuously differentiable, let me mark this as 2. So from 2 we say that partial derivative of u with respect to s, I am writing this as ux, vx, uy, vy, all these exist and are continuous in D. These are continuous in the domain D. And what are the conditions for the Green's theorem? Again, I am repeating that. Green's theorem requires the continuous functions, right? So here also we are having all these to be the continuous functions. And because all these are continuous function, so I can use this result for the line integral fz dz. For the line integral fz dz, I can use this result, this format. Okay, let's use this. So from 1 we have the line integral of fz dz to be equal to u dx minus v dy. We have marked this equation as 1 here, right? So from 1 I am writing this first equation again, is plus iota times this integral. And now we are going to apply the Green's theorem over here. So that is equal to, this line integral is changed into the double integral, right? First, this is partially derivated with respect to x, then minus this function is partially derivative with respect to y. So first we have to write the partial derivative of the coefficient of dy with respect to x. So this is equal to the double integral over the domain. What is the coefficient for dy? It is minus v, right? So writing this minus partial derivative of v with respect to x, then minus partial derivative of u with respect to y, and then writing here dx dy plus iota times the double integration over domain D, partial derivative of u with respect to x minus partial derivative of v with respect to y, right? Okay, because I need to get the answer 0, what I have to do is, because these two are not same, but here I am going to use a Cauchy's Riemann equation so that these two cancel out, right? Okay, so it is the double integral of writing partial derivative of v with respect to x as it is. What is partial derivative of u with respect to y by Cauchy's Riemann equation? Partial derivative of u with respect to y is negative of partial derivative of v with respect to x. So writing here, already I am having negative sign, also we have the value to be negative of partial derivative of v with respect to x, dx dy. So the sign changes and it becomes plus. So now these two are same and opposite to each other, so I'm cancelling this. We have 0, right? We have 0 over here, and then plus iota, double integration. Here writing again first term as it is. Here also you have to write first term as it is, changing the second one. And here also writing first term as it is, and we will change the second term. So writing first term as it is minus partial derivative of v with respect to y. Partial derivative of v with respect to y is partial derivative of u with respect to x. So partial derivative of u with respect to x. So these two are same and opposite. So I am also cancelling this, and this is also 0. Reason, we have used the Cauchy's Riemann equations, using CR equations, that is the Cauchy's Riemann equation. So this implies we get the line integral of fz dz over the closed contour C to be equal to 0 plus iota times 0, that is equal to 0. So here ends up our proof. So we have shown that line integral of fz dz over the closed contour in the domain D is, this is a closed contour in the domain D, is 0. So the line integral of fz over C over the closed contour in the domain D is 0 by making the use of the Green's theorem. Alright, thank you.